Good evening, everyone. Thank you for coming out tonight to our first ever TedxUChicago 2016 Salon. My name is Padra Tepkanjana, and I am one of TedxUChicago's student speaker salon chairs. I am greatly excited and very honored to be joined tonight by Professor Wendy Freedman and Professor Michael Turner. Wendy Freedman is a John and Marian Sullivan University Professor of Astronomy and Astrophysics at the University of Chicago. Professor Freedman joined the faculty in September 2014, following a distinguished 30-year career at the observatories of the Carnegie Institution for Science in Pasadena. Among her scientific achievements at Carnegie, Professor Freedman was a principal investigator for a team of 30 astronomers who carried out the Hubble Key Project to measure the current expansion rate of the universe, an effort that began in the mid-1980s and completed in 2001. While the Crawford H. Greenewald director of the Carnegie Observatories, Professor Freedman initiated the Giant Magellan Telescope Project and served as its founding chair from 2003 to 2015. The GMT will be a 25-meter optical telescope, poised to be the world's largest ground-based telescope when it is completed in 2021. Michael Turner is a theoretical astrophysicist and the Bruce V. and Diana M. Ronner Distinguished Service Professor at the University of Chicago. He is also director of the Copley Institute for Cosmological Physics at Chicago, which he helped to establish, and the past president of the American Physical Society. Turner helped to pioneer the interdisciplinary field of particle astrophysics and cosmology, and with Edward Kolb, initiate the Fermilab astrophysics program. He led the National Academy Study Quarks of the Cosmos that laid out the strategic vision for the field. Turner's scholarly contributions include predicting cosmic acceleration and coining the term dark energy, showing how quantum fluctuations evolved into the seed perturbations for galaxies during cosmic inflation, and several key ideas that led to the cold dark matter theory of structure formation. We will now begin by screening Professor Freedman's TED Global 2014 talk. This new telescope might show us the beginning of the universe. Enjoy.
So what's going on with GMT? Why don't you give us an update on where the project is now?
So actually, there's been a lot of progress since that was filmed. I mentioned that the fourth mirror was about to be cast, and that has been cast. At the point when I was speaking, we were in the middle of trying to negotiate an agreement, a legal basis for the partnership to go ahead for construction. And that was negotiated, and 10 partners signed a document that allows us to move forward with actually doing the construction for the project. So that was a huge step forward. On the mountain now, there's a considerable amount of activity that's happening. The dormitories for the workers that are going to do the construction, that's now underway. And the polishing of the second mirror will happen shortly. So it incrementally continuing to push forward and keep on schedule.
And there was a big event in November. The president of Chile,
Yep.
Tell us about the big...
We had a groundbreaking ceremony of this. And the president of Chile, Michelle Bachelet, came, and it was an opportunity for people within Chile to actually see the construction beginning on the mountain. And on Las Campanas, which is the site, there are some rocks where the reason for the name of Las Campanas is it means in Spanish, Las Campanas are the bells. And there are rocks that ring. So we had a giant rock, and the president of Chile was able to ring the bell and inaugurate the telescope. So officially, we've started construction. So it was a very, very fun event.
And I just, now how many students do we have here? A lot of students. So do you all know your University of Chicago history? So where did Hubble get his degrees? Okay, so if I ask more questions like that, you know the right answer. So we're building the biggest telescope, but give us a little background on, this is not the first time Chicago has done things like this. And
so going back to, I don't know if you know the name George Ellery Hale. And George Ellery Hale was the first chair of the Astronomy and Astrophysics Department at the University of Chicago. and started astronomy and astrophysics here. He then was lured out to the West Coast, and he is the astronomer that began the building of the telescopes at Mount Wilson and at Palomar. And that's Edwin Hubble, who did his degree here, and then was lured out by Hale to the West Coast, and where Hubble made the discoveries of other galaxies in the expanding universe. And so Chicago, subsequent to that, built up a very strong department in theoretical astrophysics, in studying the background radiation from the Big Bang. It's a world leader there. But in optical astronomy, it became involved in survey telescopes, but large optical telescopes were something that Chicago really had not participated in until now with the GMT. It's a full partner in the enterprise, and then you lured me back out here. So
I know you're new to Chicago, and you may not know all our mottos, but you know one of our mottos is, I know it works in practice, but does it work in theory? You all know that, right? Can anyone get me that T-shirt? Raise your hand if you can get me that T-shirt and see. Okay, so we're famous.
So you've understood already that Michael lives in a fantasy world that is theory, and and it's our job as observers to make sure that they stay grounded in reality.
So we're very proud of Hale, who 4 times built the largest telescope. And for those of you who wander south of the Midway, have people been to the Oakwood Cemetery? Oakwoods. It's really an amazing place. It's I forget if it's 64th or 63rd. Hale is buried there. William Rainey Harper, Jesse Owens. But back to astronomy here.
And of course, Hale was the person who built Yerkes, and we didn't mention
he built
that,
Yerkes,
which was at the time the
that was
biggest
his
refractory telescope of the
largest
world.
telescope. And famously, another part of University of Chicago history is that he was very entrepreneurial. Is that a word you associate with the University of Chicago? Very entrepreneurial. And so he went to Harper after building Yerkes, which was a 40-inch telescope, the world's biggest telescope. And he said, the future of astronomy is in the hills of California. And Harper said, I wish you well. And but now we got Wendy. I think it was a good trade, you know. So I wanted to ask about, you were talking about the exquisite resolution of GMT, and talking about seeing that dime, I think it was a dime, from Rio to Sao Paulo, which would be quite a trick given all that wiggling atmosphere. So, did people notice those green lights coming out from the telescope? And normally you think of telescopes collecting light. So tell us a little bit about how that extraordinary, how you get that extraordinary resolution, because I think most people know that the atmosphere wiggles and that's why stars twinkle. And tell us about that.
Yeah, so that's been the real limitation at building telescopes on Earth, and why we did so much better after the launch of the Hubble Space Telescope, is we get above the atmosphere and the blurring that's caused by turbulence in the atmosphere. And so what astronomers have developed in the last couple of decades is a technique called adaptive optics that allows you actually to change the shape of your mirror. And those green lights, yellow lights that you could see coming out of the telescope are lasers that we use, that are sodium lasers that shine up into the atmosphere where there's a layer in the atmosphere itself of sodium atoms. And those are reflected back down, and they act essentially as artificial stars. And if there were enough stars that were bright enough in the sky that we could have a star in each of the fields we were observing, we wouldn't need the lasers. But they act as a good substitute for a star. And then that information comes back down at the speed of light very fast, and it allows you then to deform the mirror and change its shape so that you can correct for the turbulence in the Earth's atmosphere. And that's what will allow us to get this factor of 10 increase in resolution compared to what we can do with Hubble. So it's a huge leap forward compared to what we've been able to do before.
And it's a complicated system.
It's a complicated, very complicated system.
And could you actually...
these mirrors are very thin. So in fact, the corrections are done with the secondary mirrors. So the The mirrors that I was talking about being made at the University of Arizona that are 8.4 meters in diameter, each one of those 7 mirrors will have a secondary mirror, which is near the top of the telescope.
And we saw I think we saw
saw
that. Those,
in the,
they're about yay big or something.
yeah, they're about 1 meter in diameter, and they're much thinner, and because they're smaller, they can be deformed much more quickly. And the primary mirrors will have essentially pistons that you push and pull on the back of the mirror and change the shape of the primary mirrors at various points. There'll be 4,700 of those actuators on the back of the primary, and that's updated every 30 seconds. But the secondary mirrors will be updated on a millisecond time scale. So that's what allows you to make these really rapid corrections to correct for the turbulence in the Earth's atmosphere.
So that's really a big deal. That's what gives it, but you know, not to get, so I was whispering in Wendy's ear, so could you really, are the adaptive optics good enough so that we could actually see that dime in Sao Paulo?
Yeah, well,
you could
first of all, we wouldn't point it to the horizon.
Yeah.
We wouldn't actually observe in Sao Paulo. But yeah, we could do that. In principle, that's achievable.
So one of the things that you know, we do at the University of Chicago, so exoplanets, everybody knows about exoplanets. Those are planets around other stars. And we've got, what, 2 faculty members and a third one joining us. Leslie Rogers is going to join us. And so
I know at least one student out here has had Jacob Bean as a professor and studies exoplanets.
So the what will you know, it's technologically very exciting and challenging to build the GMT, but of course that's not why we're doing it. We want to do it to answer big scientific questions, and one of them is this question about, are we alone? Are there other planets that harbor life? And so maybe we should talk a little bit about what, you know, where we are on that and what GMT can do.
So one of the immediate things that GMT will be able to do is, right now there are candidate planets, exoplanets, that have a mass comparable to the mass of the Earth. And I say candidates because there's nothing sensitive enough right now that could actually measure a mass that's as small as the mass of the Earth. Jupiter's and Saturn's, they're more massive. Even Uranus and Neptune now, it's possible to measure those masses. But to get masses, you need velocities. You actually have to measure the orbits of those planets. And that will require GMT. And it will be the first telescope that will have the capability of actually measuring a velocity of an Earth mass planet. So that would be the first thing, is to actually establish that there are planets with the mass of the Earth. Then it will be possible, because of the size of GMT and its sensitivity, you can actually disperse the light, not just measure a velocity, but actually measure the chemical composition of the atmosphere of the planet. So if there are things like water and ozone, carbon dioxide in the right ratios in the atmospheres of these planets, GMT will be able to detect that. So it will be capable of looking for signatures of life. And then, and I'd say this is next generation, it won't happen in the first generation, but actually imaging a planet. And that's not to say that we get, you know, the big pale blue dot, or, but because these mirrors are so precise, you can actually, once you know what the orbit of the planet is and where it is, you can mask out the central star that the planet's orbiting around and then actually image the planet itself. And that would be a really exciting discovery. So there are a lot of places where GMT, in fact, the atmospheric measurements, no other telescope that's even being planned right now will have that capability in its first instruments to be built on those telescopes.
So we'll have an undergraduate lab imaging Earth-like planets around other stars in what year, 2025 maybe?
Sure.
Okay. And, you know, one of the things that I find, I mean, we're both cosmologists, so we do the big picture, how the universe began and all that. And so we'll get to that, but we feel like, you know, how many people are interested in exoplanets? Yeah, okay, so maybe how many people have heard of Planet 9? Okay, maybe we should. So one of the most exciting things in exoplanets, to me, and is that we had no idea. We were certain that there would be other planets around other stars, that just because of the numbers you gave, 10 to the 100 billion galaxy, 100 billion tries in each galaxy. And we had no idea what it would be like. I mean, the simple thing is, well, it must be 9 planets or maybe 8 planets. And of course, what we found...
And big planets, or small planets,
inside,
then big planets, they're all on a plane.
Same. And so what did we find?
That the other solar systems are not like that. And essentially, the predictions were you could never have a planet as big as Jupiter in close to its central star. And Jupiter has a very massive gaseous atmosphere, and the predictions were you couldn't have that much gas, it'd be blown away by the parent star. And the first planets that were found, in fact, were just like Jupiter, essentially, but really close in. Orbiting.
Closer than Mercury.
Yeah, quite extraordinary. And many of the planets have orbits that are inclined to the plane, just orbiting in the same direction, and as the central star is rotating. And so that was a surprise. And now it turns out that maybe the most common type of planet has something like the mass of Neptune. It's more massive than the Earth. And so most of the solar systems that have been discovered really don't resemble our own.
In fact, it was exactly what you're saying, is the surprises. Until you go out there and look, or ask a really smart theorist.
Yeah, I was being polite. I didn't say that theorists had predicted that we shouldn't find any of what we did.
But for me, one of the interesting things that we've learned, so we're learning about these exoplanets, but of course then we learn about our own solar system. And so one of the things we've learned is that the planets move around. So these they're so-called hot Jupiters aren't always there. They go in, they go out. And so one of the things, I'm not an exoplanet guy, but I talk to our exoplanet guys and soon gals, and the following statement they believe is true, is that the number of planets in our solar system has changed. We've lost some. There undoubtedly in the past were more. They've moved around. And that brings us to planet 9, which is it was discovered in California, so you
I left California, but yeah. So for those of you who haven't read about it, a few weeks ago, prediction by an astronomer at Caltech and his colleague that there should be another planet way far out in our own solar system, and the way that they're inferring that it's there is there are some rocky bodies out in the outer part of the solar system, the so-called Kuiper belt, and the orbits of those are...
Let's see, where was Kuiper? What was his institution?
University of Chicago.
Oh, okay, just checking.
And so, as you recall, Pluto got demoted. It got flung out of our own solar system. It's a dwarf planet. It doesn't have the capability of clearing out the area in its vicinity. And the orbits of these other Kuiper belt objects that have been found in recent years seem to suggest that there's something out there that's perturbing them and that's causing them to have the orbits that they do. And so this thing is predicted to be very massive. I think it's 10 or 20 times.
Like a Neptune.
The mass of the Earth. And it's not seen yet, so it's not an actual discovery, but it appears to be inclined about 30 degrees to the plane of the solar system and out there waiting to be discovered. So it's got the community really thinking about how to go out and search for it. It would be very faint, it's very far away, but it suggests that there are actually 9 planets in the solar system after all, if they're correct.
And it's a wonderful story because we had this picture of a static solar system and neat and tidy, and actually they move around and we've lost some, and so now there'll be theories about how did Planet 9 get out there and what's the story about Planet 9 and
what perturbed it.
Was there Planet 10, but it went bye-bye, and then the other thing that's really fascinating, you brought up Jupiter, is that, and you brought up the habitable zone, that so we don't know precisely what you would need to have a planet where you could have life. So water is a simple one. We think now a Jupiter that is kind of a protector that keeps you from getting bombarded by asteroids and things, that shepherds them away. What are some of them? Well, I guess you want a star that lives a long time and is pretty quiescent, so it doesn't Well, there was that movie about Waterworld that, well, maybe we are alone. How many people think we're alone in the universe? No one.
Ooh,
Everybody
0.
thinks there's other life in the universe? Is there another University of Chicago in the universe? There's only one University of Chicago. Well, maybe we ought to, exoplanets are okay, but cosmology is really cool. And you mentioned dark matter. And so maybe we should talk about dark matter. And in cosmology, we're very excited because we know what the universe is made out of. And it illustrates what Wendy was saying about these surprises. So we have the ingredient list for the universe. It's 5% atoms, it's 25% dark matter, and it's 70% dark energy. And atoms, I bet everybody knows about atoms. That's what we're made out of. Does anyone in the room know what the dark matter is made out of? Good.
Darn, could have had a Nobel Prize.
Yeah. And then the dark energy is even more mysterious. So we're at this point in time where we've got the ingredient list, but we don't quite know what the pieces are. And maybe we ought to start with dark matter because you mentioned it in the TED Talk, and then it just came up, you mentioned it again. How can you, with Planet 9, and because astronomy is, the universe is so big we can't go there, so it's based on what we can see. And so if you can't see it, how can you really see it? And what?
Yeah, so in the same way, so in fact, in our own solar system, the existence of Neptune was predicted because the orbit of Uranus was, had a discrepancy in it. If there hadn't been something else.
It didn't agree with theory. I think that's.
That's right.
And the theory was correct? Is that what I'm?
Yeah, but
okay.
you could count that
Just
one,
checking.
but there was Vulcan. There was another planet. There was a 10th planet, in fact, inside the orbit of Mercury, predicted by theorists.
Yeah.
But that turned out to
Not
be...
at Chicago.
Another theorist got that one right, though, because
Yeah.
it was Albert Einstein that predicted the change of the perihelion of Mercury. But anyway, sometimes you learn something else, but theoretical predictions and then interface with observations. But in the 1930s, an astronomer at Caltech noticed that when he looked at the motions of galaxies in a nearby cluster called the Coma cluster, they were moving too fast. If you added up all the mass in the cluster, then those galaxies should have been long gone. They wouldn't have been bound to the cluster. Essentially, nobody believed him then. It was too strange.
It's too bad we don't have a picture of him, because if you showed his picture, you would know why no one
believed him.
He was a very cantankerous guy who was half as smart as he thought he was, which was still deadly smart. But he didn't.
Are we allowed to say what how he described his colleagues in this audience?
Oh, yeah.
So his colleagues at Caltech, the other faculty member, he described as spherical bastards. Why? Because they were bastards no matter what direction you looked at them in. So, so it gives you some idea of the kind of personality he had. But it wasn't only that. It was a very strange result. And this was the 1930s. And it wasn't, and in fact, other people in the 1930s, Horace Babcock, discovered that there were stars in the nearby Andromeda galaxy that were going faster than they should be if they were bound to the galaxy. And then Vera Rubin in the late 70s and her colleague Kent Ford observed a lot of spiral galaxies and noticed that the velocities of the stars in the outer parts were much faster than they should be, indicating, again, the presence of some matter that was causing these stars to have the motions that they did, but we couldn't see it. And then in the 1980s, it became possible to measure X-ray gas in clusters. So this is gas that's maybe 100 million degrees and should have evaporated long ago if it was unless there was more matter in the cluster that was binding it. And then people started to see these big arcs that were predicted, in fact, by Einstein, the bending of light as it's coming through a massive cluster.
Einstein, the theorist, right?
Einstein, the theorist,
just checking.
And eventually, the evidence became overwhelming. There is just more matter there than we can see. And in fact, there's 6 times as much of this dark matter as there is visible matter. But we don't know what it is. And in the 1980s, astronomers spent a huge amount of time trying to rule in or out the obvious things. Could it be black holes or dust or gas, cold gas, hot gas, failed planets, failed stars, you name it. And none of those things could explain what was seen.
And this is where we cue in the theorists.
Here's your cue, Michael.
So this is, and the University of Chicago theorists said, you know what? We think this is not atoms, it's something more exotic. It's a new form of matter. And we now have evidence that we have an accounting of the atoms in the universe, it's 5%, and the total amount of matter is 30, so 25 plus 5. So 25 can't be atoms. And so we think it's a new elementary particle. And that's an idea that my mentor, your close friend, David Schramm, first he started with neutrinos, but we've ruled out it being neutrinos, but we think it's another particle. And this is a big activity at Chicago. Chicago's involved in trying to produce this particle, this dark matter particle at the LHC in Switzerland. So at a particle accelerator, or detecting it, because if this idea is correct, then in this little bottle, there's one dark matter particle.
Well, they're going through you right now.
Yeah, they're also going through you, but I didn't want to scare people. And but you
Remember,
need
I told you it interacts very weakly. We can't find it.
They're very shy. And so we're building detectors underground to try to detect this. And so this is very, very exciting. And if you think about it, we've pushed ourselves into a corner without going through all the evidence where that's the most conservative hypothesis, is that it's a new form of matter. Anything else would be more radical. Most conservative is not always most correct. Maybe we'll even find that out tonight. But that's the conservative hypothesis, is it's a new form of matter. And now we're on the cusp of having to verify that, and it's an interesting time. So people have been searching for this now for well over a decade, a couple decades, and haven't found it. And now it's getting to the point where it may become impossible, at least the current best ideas. It's getting hard, and maybe we're in for a surprise. Maybe it's something wrong with gravity, or
theorists.
Or theorists. That I doubt. But let's go back to Vera Rubin, because in the very beginning of the TED Talk, you brought up this issue of women in science, and of course there's been a lot of change.
Any women scientists out here tonight? Anyone?
Ah, there we go, at least one. And there's been a lot of positive change, and we can recruit for astronomy because sometimes it's the young fields, where change is happening, and you don't have to be a member of the old boys club to make a contribution. And Vera Rubin is one of the pioneers, and she tells this story that she wanted to go. Now there's a school, I always forget the name. There's a little boys finishing school in New Jersey. What's that one in? Is anybody? The boys finishing school in New Jersey. Some of you might have applied there. College of it. Where? What's it? Do you remember?
Princeton.
Oh, Princeton. Princeton. So she applied to graduate school there, and they wouldn't even send her a catalog. I think I've heard her. I'm sure you've heard her say this story. They wouldn't even send her a catalog because they didn't want to waste the money, because girls can't be astronomers. And so she actually got her PhD at George Washington University from someone who we won't talk about because he's so interesting, and George Gamow. And so here she is. And I was at an event where she described, this job she had. I think she didn't get paid as much as the other. How did that work when she went to work for the Carnegie and didn't get paid?
She walked in and told the director she wanted a job.
And she would work for free or something.
Yeah, and then he did pay her, but not as much as, that was Cecilia Payne-Gaposchkin, who was a faculty member at Harvard. She was paid 25% of what her male colleagues were paid. And then she eventually became chair of the department. And I think it was finally corrected. She probably corrected it herself, I'm not sure.
But Vera then...
But that even happened to me when I was hired. I was paid half as much as the man who got hired at the same time as I was.
You think that's
But
still
then I was a Canadian citizen.
Well, that's
at the
the
time.
real problem.
That was the real problem. Well, the immigration helped me because my job salary had to then be posted. And then every male faculty member came to tell me, do you realize how little you're being paid? And I never would have known if I hadn't had the immigration issue. So that's that still happens.
And who's the chair of our department?
No, that was a long time ago.
But now.
Now it's Angela Olinto.
Yeah. Although she's, even Chicago doesn't get high marks on this. So she's the first woman chair in astronomy. And you might say, well, but she's the first woman chair in the physical sciences at the University of Chicago. So.
And I was the first faculty member in 100 years at the observatories in Pasadena, and then the first woman to be director. So a lot of firsts still. It's unusual.
For the young lady back there who was interested, so you go to an astronomy meeting, and it looks like high school. Is that a good description?
Elaborate.
Well,
no, I'm not sure I know.
Everybody's younger than you, not than me. I'm quite young myself, but and everybody's high energy. But it's very diverse. Lots of women. I mean, astronomy. The PhDs in astronomy are essentially close to 50%.
Yeah, it might be 30 still.
The PhDs or the.
I don't think it's yet.
Not quite 50. Okay.
Yeah, but it's getting there.
Do you have any good, I know you've got at least one, I shouldn't say this because now you'll have to tell it, some good horror stories about being a woman astronomer, going to the mountain and stuff like that.
Oh, gee, going to the mountain. Well, it didn't happen to me, but at Carnegie, which had this fellowship, one of them was the Hale Fellowship, in fact. And if you applied for it, you were told that they didn't give them to women in the same way as Vera Rubin encountered. What could I tell you? Luckily, that changed by the time I got there.
But going to Palomar, didn't they play some tricks on you or something in the...
I think you're thinking of Margaret Burbage because at that time, there was another astronomer. She was married to a theorist, and women were not allowed to observe on the telescope at that time. So he had to apply for the time, and then he had to sit on the observing floor.
To make sure she didn't break the telescope.
Yeah, but the excuse that they gave was that there were no restrooms for women, and that's why they couldn't have them come to the telescope. And so he had to guard the door while she went to the restroom. So it was slow in coming, but yeah, it's really changed now. There are a lot of women in the field, and it's really nice to see.
Well, and so just another Chicago footnote to that. So among other things, Wendy actually has an honorary degree from the University of Chicago, as does Margaret Burbage. And Jeff Burbage, her husband, actually, who is a very brilliant theorist, but he does not have an honorary degree from the University of Chicago, which is fine. Well, not everyone can have a degree from the University of Chicago. Do you have anything more on that topic? We're ending on a high note, but do you?
Let's see. No, I just thinking now of, so I did my thesis at the Canada-France-Hawaii Telescope in Hawaii, Mauna Kea, which is at 14,000 feet. And The telescope had just been commissioned when I went out to observe, and I couldn't figure out why there are people following me around and asking me, "Are you okay? Can you breathe?" as if I was some sort of a helpless something. And I finally said, "I'm fine. You don't need to keep asking me." But it turned out that in the a couple weeks before, they'd had a big event, and they'd brought up some Marines for the commissioning of the telescope, and they both fainted dead away. So that if the Marines can't hack it at 14,000 feet, there's no way this woman's going to be able to hack it. But I never had any trouble observing it at high altitude. It was fun. So it's an interesting life. It's different. It's fun.
Well, before, I think at some point here we're going to, do you guys have questions? Good. Well, we're going to go to them, but we'll do one more thing before we go to the questions, and maybe we'll talk about the 70%, the dark energy. And let's see, well, I know it's there, but maybe you ought to tell us why, what evidence. I mean, I hear evidence is really important in science. Actually, it is really important. That was just meant to be a joke. But so how do we know there's dark energy?
So that's one of the things that came pretty much out of the blue again. People didn't expect it. Or there were two groups in the 1990s that started to observe very bright explosions called supernovae to greater and greater distances. And we know that there's matter in the universe. It became increasingly clear that there's dark matter in the universe. And so the expectation was that, so we didn't really talk about the expansion, but Edwin Hubble in 1929 discovered that the universe is expanding. So we see the effects of that expansion today, and that's the work that I did a couple decades ago, was to measure very accurately how fast the universe is expanding. But we expected that as we looked back farther and farther out into the universe, we would see a time when the universe had been expanding. Earlier on, it would have been expanding faster and then slowed down because of the effects of gravity. So, we know that if you throw something up in the air, right, it's going to fall down because of the effect, the force of gravity, which is an attractive force. But instead what happened was the supernovae appeared fainter, as if the universe had been speeding up rather than slowing down over time. And so, that really was a surprise, because it would be like throwing up something into the air and then it takes off even faster. And so we weren't expecting to see that. It actually was something that had been predicted by Einstein. I'll turn it over to you to sort of take over that part of it. What happened in the intervening time was it appeared to be evidence a few times, and then the evidence didn't hold up. And so people were very skeptical about this, because it also was very difficult to explain, still difficult to explain. But why don't you describe that part of it?
So the explanation is dark energy. So let's just say it that way, and then we'll see, is anyone still confused? And so the explanation is there's this stuff called dark energy, and it has repulsive gravity. And you might say, well, I don't get that, because, isn't the essence of gravity that it's attractive? And in Einstein's theory, really weird sorts of energy can actually have repulsive gravity. So it's in his equations. And then comes the checkered history. So you have to trust me on that. It's in his equations that if you have really weird stuff, we call it dark energy. It has repulsive gravity. And so the simplest explanation is that the universe is 70% dark energy. So that's an explanation. It may or may not be true. But then the checkered history is really interesting, because, so give me an example of dark energy. And the simplest example, I bet everyone or many people in the room have heard this word, the cosmological constant. So Einstein put into his equations something he called the cosmological constant to keep the universe from expanding. And you might say, well, why would he do that, since Hubble discovered that it was expanding? And that's a whole nother story about the fog at the frontiers of discovery. As you're out there, and it's really confusing, even to really extraordinarily smart people.
Einstein came up with his theory in 1915, and Hubble didn't discover the expanding universe till 1929.
And there was every evidence that the universe was static. And but even after Einstein got his solutions, he didn't really realize it was confusing. He didn't even realize they were expanding. And so he put in this term to balance it, to balance matter, and then threw it away. And then every time there was a crisis...
And threw it away because of Hubble's observations.
That the universe was... And the fact that he became convinced that his theory really predicted an expanding. It's really confusing. But then probably every 20 years, cosmologists would put in, anytime we had a serious problem, we'd put in the cosmological constant. And you got a problem.
And then it would go away,
And then it would go away. And the most recent one was in the 90s, where actually Wendy and I really got to know each other very well, because the theorists predicted that we have a flat universe. What's the shape of the universe that's actually been measured, just to check?
Flat.
Flat. Oh, okay. But there wasn't enough matter to make, there wasn't enough...
But they weren't right about what made it flat.
Well, that's, okay. I get to tell my part of the story. So he
was closer than most.
we start simple and say it's matter, and it turned out we didn't know the amount of matter very well, and the matter stocks were really rising, just like the market, and it looked like they were going to hit 100%, and there was a market correction, and it came down to 30, and so there are the theorists. We had really good arguments that you should have a flat universe and you should have the so-called critical density to make it flat. And so a couple of us came up with the idea again of the cosmological constant. And then others came up with the idea that maybe the Hubble constant was very small, but that's another story. So it turned out to be one of those, I could like to call it the most anticipated surprise, in the sense that it was out there, but it was too crazy to be true. But then it turned out to be true, and now we have to figure out what it is, because we really don't. We have a name for it, but it's like dark matter. We don't really know.
Michael gave the name for it.
Yeah, and we really don't have any idea what it is. In fact, it's even worse than that. We have one idea for what it is, and it's an extraordinarily good idea. It's the energy of nothing, the quantum energy of the vacuum. And so you might say, well, that sounds really good. And so the quantum energy of the vacuum, that sounds really good. So that's virtual particles in the vacuum. So does it give the right answer? And the answer is pretty close.
Close enough for theorists.
Yeah. So it's only off by 55 orders of magnitude. And so now we sort of...
biggest discrepancy in all of science.
Well, so this is where theorists get really defensive, is that, well, actually, Wendy, our prediction is infinity, and infinity is not a number. How many mathematicians do we have in here? So you all know infinity is not a number. So if you got infinity for your answer, you didn't really get an answer, so you couldn't have gotten the wrong answer. And so,
nice try.
yeah, I see the smart ones in the room get that argument. So anyway, it's a very, very big puzzle. And remember, why are we even interested in this? This is more than 2/3 of the universe. It controls the destiny of the universe. So this is a big, exciting time. And I'll just mention one thing, and then we'll go to your questions. So another activity at Chicago is the Dark Energy Survey. And so that's a big project where we're trying to figure out what the dark energy is. And we don't have time to talk about that. Maybe somebody will ask.